Okay. And then, okay, so it's doing the thing. When does it show? How does it? Oh my gosh. Okay. Oh, okay. Ad hoc capture. Got it. Got it. Okay. All right. Thank you so much. All right. You have a great day. Really appreciate your time. Okay. Bye. Thanks for bearing with us.
No.
I just really wanted to sort that out if there was going to be a proper issue. Okay. Which there was. Make sure everybody knows. Okay. All right. Hello, everyone. Thanks for your patience there. I think we're good to, I think we're all good now. Let's take a couple looks real quick, make sure that's all good. Should be good. Okay, all right. Hopefully everybody's finding it okay. What a momentous start to the semester. Oh. Thanks everybody for your patience. So, hopefully everybody's finding and tuning into this okay. Oh, all right. So, let's get started then. So, event-driven computing, where are we up to? Wow, that's thrown me for a loop. DFAs and NFAs. Okay, well, let's start off with a bit of a quick update on everything that's happening in the course. There's not a lot happening at the moment because we're just starting out the semester and we're sort of easing our way into things. So first couple of things, programming assignment 1 will be available on Friday. It will be due at the end of week 6, so you have plenty of time to do it. We'd like to have made it available a little bit earlier, but we're still having a few bits and pieces in terms of getting the grading system up and running because we're using a new grading system this semester, and there's still a few cogs in the pipeline or something that need working out before that can all go live. So Friday this week, that'll be up. Workshops start next week. Hopefully that all makes sense. And just as a side note, making sure I'm on the right darn tab here, feel free to go ahead and ask questions throughout this session, either in Echo 360 or in the live Q&A that is happening in Piazza right now. Both of those are available, live Q&A or Echo 360. I'm watching both of those. So hopefully, even if you are joining us for the first time this week because you've only recently enrolled in the course, you've gone over all the admin stuff, so you're familiar with the idea that we won't actually be introducing new concepts in these sessions. Instead, we're going to be diving into the things that we've already read ahead of time. So the pre-reading for today's session was chapters 0, 1, and 2 of the Notes on Finite State Machines. You'll find those in the course readings if you aren't already familiar with that. And now if you're here and you haven't read those, that's okay. Hopefully this stuff will make a reasonable-ish amount of sense, but if not, you may wish to either pull those up right now and take a look, or look at those and then come back to this in post in the recording, once the recording's up. Okay, all right, so things that we want to be looking at today. Finite state automatas, alphabets, strings, DFAs, how we model DFAs, string matching, NFAs, NFAs being different from DFAs. I don't think we're going to get through all of this since we've lost half an hour already, but we'll see how we go. So we have a variety of different examples and exercises that we want to work through to get a bit of a feel for how all of this comes together. Hopefully, again, you've read the notes, you're familiar with the basic concepts. Now we're going to try putting them into practice. So, to that end, let's start off with a basic example or exercise. For those of you who are watching this live, go ahead and we'll take 5 minutes to have a crack at some of the basics of this exercise, and then go ahead, post your answers that you have in the Piazza live Q&A that's happening right now. So to start off with a basic FSA exercise, I don't expect you to actually implement any code for this, and we'll talk about the practicalities of implementing code for this in a couple weeks' time. But just to start off with, we want to model a basic system for an electric door. It has a button. You push the button, it opens the door. When the door senses that it is fully open, it's going to stop. So there's some kind of sensor or trigger that indicates when the door is fully open. And then when we push the button again, that's going to close the door. Again, there's another sensor or trigger that notices when the door is fully closed. The door is going to stop when it's fully closed. So push the button, door opens, door stops once it detects it's open. Push button again, door closes, door detects when it is fully closed. Let's try modeling this out using a FSA. So 5 minutes, have a crack, post your basic, now you can go for either a transition diagram, a transition table, or if you really want to have a crack, you can go for the 5-tuple representation of the system. We'll take a look at all three, but have a go at that, 5 minutes, and we'll see where we end up. And again, feel free to post questions in either the live Q&A for this session right now, or in the or in Piazza. Or in Piazza. I realize now that while paused, the question itself is not visible, so I'm just going to leave it unpaused for the moment. how's it looking?
I just realized something. Yeah. So it's like you have to remember whether or not the last time you clicked the button it was opening or closing, I think.
Yes.
Yeah.
Yeah.
So I'm trying the 5 tuple answers, but how do you think?
Yeah, the 5-tuple representation always messes me around. It's one of those things that if you can remember what the things that need to go into it are, and if you can remember whether you're dealing with at any stage a set or a single item, then the 5-tuple representation should be fairly straightforward, but it takes some remembering. I can never remember the actual full 5-tuple off the top of my head. I think we start with Q,
Yes.
then Q naught. It's uppercase Q because it's a set, lowercase Q naught because it's a single state in a DFA, assuming that we're working with a DFA.
Was it Q naught?
Then it's delta. I'm not entirely sure if the order is
Okay,
super
sure.
important, but as long as they're all in there, I think that's the most important thing.
Yep.
And then capital F.
Yes.
Hang on. Q naught. I'm missing something. Q naught delta capital F.
The alphabet?
Oh, the alphabet.
Yeah.
Is that sigma? Is the alphabet?
Yes. This thing.
Yeah, sigma. Yeah. I should actually check the notes to see which order they're supposed to be in.
Yeah. I'm trying to remember order because it helps me remember. So if I know if I can.
All right, so hopefully that's enough time for at least people to make a bit of a start. Feel free to post your solutions to this or your progress to this in Piazza as you go. You can post anonymously. I'm not showing who's posting what, or actually I'll make sure I switch to hidden view where we can't see who's anonymous, so that if I do show these, we can stay anonymous. While people are working on that, let's just have a crack and see what we end up with. So, we can zoom that out a little bit, I think. Okay, so to start off with, we probably want to identify our set of states. So there's a few things that we need to identify for a system like this. So our objective here is that we want to try and represent the system as some sort of DFA or FSA that represents all of the different states in which the system can exist at any point in time, and then represents the transitions between those states where, again, the transitions represent the individual events that occur within the system. To do that, we're going to need to identify our set of states, the alphabet of the system, or the set of transitions that we have, or the set of events that we have effectively. A transition function, our initial state, and a set of final or accepting states, noting that the system may not necessarily have a set of final or accepting states because not all systems need to have accepting states. That'll make more sense when we start looking at string processing, which hopefully you're roughly familiar with already. But let's start off with a basic system. We will probably want to, and there's a few different ways that we can approach this, but let's just start by identifying all of the different states that the system can be in. For those of you who are watching live, and I see that there's about 15 of you at the moment. Yep. So for those of you who are watching live, can I just get a quick poll either in Piazza or actually, hang on, I'll put it in Piazza. What are the states? All right. So I've just posted in the Piazza live Q&A. What do we think the states are for the system in the first exercise? Again, I'll quickly hop back over to the description here. What do we think the states are? You can go ahead and post that in Piazza. Oh, okay, what have we got? Okay, there's a bunch of people hopping on to the answer section. Yeah. Okay. Yeah, okay, that's looking good. All right, so I think pretty much everybody's got it. We've got roughly 4 states in this system. I'm going to draw this up I'm going to start by drawing this up as a transition diagram, but there's a few different ways we can represent it. So, yep. So as people have alluded to, we have closed or closed and stopped, depending on what we're doing. We have closing. Is this showing up properly? Oh, it is just way not focused. Hang on. Doop. There we go, that's better. All right, there we go. Okay, so we have closed, we have closing, we have open, we have opening. Okay, so those are the 4 states that we're going to have in the system. That's fair enough. Any rough ideas on where we actually want to initialize this system? Where do we want to initialize this system?
Maybe close so that the system knows it's supposed to be opening or push.
Yeah, yeah. We should probably initialize the system in the closed state. Absolutely. So we'll indicate that this is closed. Okay, and then so we have these 4 states, and then we need to somehow transition between them on the various different events. What is our alphabet for this system? I'll make a new post for that. Maybe I convert that to a note. Yeah, I think follow-up discussions are a bit better here. Yeah, okay. What do we reckon for the alphabet for this system? Yeah, so in terms of the inputs that the system has, so we have a suggestion here that is it just like pressing the button, and that's definitely one of the possible inputs in the alphabet, but I think that there's a little bit more to the alphabet than just the button being pushed. Can we think of any other inputs into the system? Again, I'll go back to the description so that we can look at that again. Albeit so to remind ourselves as well, so we have the button that we're pushing. The door also needs to know when it is completely open, so it's going to have some sensor or something to indicate when it is fully open, because the door's not magic. And similarly, when the door is closed, it's going to have some sensor to indicate when it's fully closed. And I think that's one of the things that I want us to get used to with this type of system. It's that the system isn't magic. It's not going to, in an event-driven system, especially when we're modeling one this way, nothing happens unless there is actually something to trigger it to happen. So pushing a button, that's definitely one of the triggers. What have we got? Yep. Yeah, okay, so we have a button, we have an open sensor, and we have a closed sensor. That's good. So, and you could call them different things if you want to. Yep. And then we just have to connect them together. So feel free to post your transition diagrams or transition tables in Piazza for this, but I'm going to go ahead and connect these things up. So if I am in the closed state, so we have, well, if our alphabet consists of, I need to select the camera. Okay, so if our alphabet consists of our button, and then it has open, sensor and closed sensor. It's like, okay, so if these are the three possible options for things that could occur within the system at any point in time, what we want to do when we're building out a DFA is we want to map out for each individual state in the system, when each of these events occurs, what actually happens when each of these events occurs in the system in each state. So let's start off in the closed state. If I press the button and I'm in the closed state, what do we want to have happen? Hopefully we all have a rough idea that we want to move to the opening state. So if I push the button and I'm in the closed state, we move to the opening state. Presumably this is going to trigger some sort of behavior to actually, turn on the door's motor to start the door opening. If we are in the closed state and either of the sensors are triggered, what do we want to have happen? Now, for argument's sake, we could probably just say that, well, if we're closed and either sensor is triggered, we probably don't want anything to happen. Like, the door just stays closed. Yeah, that would be. I mean, if this was a security door, we wouldn't want the door to magically open if suddenly one of the if the door open trigger happened to go off while the door was already closed. So we can just loop back and keep ourselves in this same state. So I'm just going to shorten this to OS and CS as open sensor and closed sensor. All right, so we've addressed button, open sensor and closed sensor for the closed state. Let's take a look at the opening state. So if the door is opening and the button is pressed, what do we want to have happen? Now I realize that this is actually undefined behavior for us. Oops, sorry, let's move that down a little bit. We might realize that this is actually undefined behavior for the system. So in this case, we want to choose something sensible for the system to do. If the door is halfway through opening and the button gets pressed again, what do we want to have happen? We have a few options. We could say, all right, let's just keep opening the door and do nothing. Maybe we could start closing the door if the button is pushed. Choose something sensible. I'm going to say that if I press the button while the door is opening, it's going to start closing. That's probably what's going to happen there. And if the open sensor is triggered while the door is opening, then we want to move to our open state. And if the closed sensor is triggered while the door is opening, well, it's probably only just started opening. We probably don't need to do anything in that case, so we'll stay right where we are. And we can finish this for the rest of the system. So if we are open and the button is pressed, we start closing. And if either sensor is triggered and the door itself is open, we do nothing. And finally, and that's all of that, so then we just fill out the closing state. So if the button is pressed and we're in the closing state, we're going to go back to the opening state. If the closed sensor is triggered, then we are there, and if the open sensor is triggered, we are here. And that is our basic system that we have for that description. All right. So with that in mind, let's go ahead and map out a transition table and maybe also a 5-tuple representation of the system. So start off with transition table. Okay, transition table. On the left-hand side, down the column, we're going to map out our states. So we map out our states, make sure we indicate what our initial state is. And then up the top here, we map out our inputs into the system, our alphabet. So we have our button, we have the open sensor, and we have the closed sensor. And then in the middle here, we fill out where we end up for I did not leave enough room here. That's okay. All right, in the middle here, we map out where we end up for each combination of a given state with a given input. So we know that if we are in the closed state and we have the button, then we go to opening. And if we're in the opening state and we have the button, we go to closing. And if we're in the closing state with the button, we go to opening. And if we are in the open state with the button, we go to closing, which matches this, yeah? So, and then we have the open sensor and the closed sensor. So again, if we're in the closed state and we get either of these, we stay in closed. And if we are opening and we get the closed sensor, then we're going to stay in opening. If we get the open sensor, we are open. And similarly, and finally, if we are open and we get either of these sensors, it's just something like that. And that's our transition table. Hopefully that's all fairly straightforward. I see some people have gone with like 1 and 0 as the possible inputs to the alphabet. You've probably seen 1s and 0s a bunch in the notes in terms of string processing, which we'll come to in just a moment. We don't necessarily have to strictly use 1s and 0s. We can name things appropriately for what we're trying to do. But I see what you're doing there, and fair enough. But no, our alphabet should be all of the possible inputs into the system, and ideally we're going to give them names that make sense for what we're trying to do. All right. 5-tuple representation. So the 5-tuple representation is a set theory. So the mathematics of set theory, it's a set theory notation for the system as a whole. Let's take a look at the 5-tuple notation. So 5-tuple notation is called 5-tuple because it is a tuple consisting of 5 elements. Those 5 elements are going to be Q, sigma, delta, Q naught, and F. So the first thing to note is that whenever we're doing set notation, which the 5-tuple representation is based on set notation, whenever we're doing set notation, the symbols that we're using can either be uppercase or lowercase. A lowercase symbol denotes a single item, an uppercase symbol denotes a set of items. So in this case, Q represents the set of states. So this is all of the states in the system. And that's going to look something like, is it squiggly brackets? I can never remember. It is indeed curly brackets, I think. I can never remember whether it's curly brackets or square brackets for this. Yeah, curly brackets. So Q, it's the set of states. So open, closed, opening, closing. Okay, so Q is the set of all of the states in the system. Sigma is our alphabet. So that's all of the possible inputs into the system, which we have the button, the open sensor, and the closed sensor. Again, it's a set, so it's uppercase. Both of these are sets, both of these are uppercase. Delta represents the transition function. It's a representation of it's a representation of all of the transitions in the entire system contained as a single symbol. So and it's a little delta. And you can't write it in one line, I think is one thing to be noted. So the way that you would write out delta is that you would write out every possible combination of state and transition to indicate what the outcome would be for each of those, in the same way that you might see in a mathematical function where there are multiple distinct functions that apply depending on the conditions that are applied to that function. You might see multiple different sets of equation or outcome that result from that. So in this case, delta for this system is going to look something like, so delta of open with button equals closing, and delta of open with OS, I hope I have these the right way around. Yes, I think so. Yes, I do have these the right way around. Is open. And you would write these out for every transition in the system, and that is what delta is for this system. So delta is like all of that. Q naught, lowercase q, because there's only one of them, is the initial state, which we know is closed. Albeit, if you made the decision that the system should start in the open state, that's also a reasonable decision as well, as long as you have good reasoning for being able to back up why that might be in the open state. And then F is the set of accepting states, which at the moment is empty. And we could potentially write with a null if we wanted to. So that's our 5-tuple representation. And we write out our 5-tuple as m equals q sigma delta q naught f, where each of those are these here. And that's that. I'm not seeing any questions. Am I missing any questions in here? No. Feel free to ask more questions if you have them, people. Is that a question? Any questions about exercise 1 there before we move on?
Can I ask a question? I guess in real life, the OS and CS, they're like sensors, and they shouldn't go off unless the door is fully closed or fully open.
In theory, yeah.
But we have to define actions for if they go off by chance in other states.
Yeah. So the question is, for those who are on the stream, the question was, the open sensor and the closed sensor theoretically only go off when the door opens, or when the door reaches the fully open state or the fully closed state. It triggers those sensors, and in theory, those sensors only go off once when the door actually arrives there. Although, depending if they were good or bad sensors, they might trigger continuously once they're in that position, but that's a bit of a technicality. So why do we have to include them in the other states? And yes, you are correct in saying that we include them so that if they do go off somehow for some reason while the system is in one of those other states, that we don't end up in a situation where we have undefined behavior. The system has a clearly mapped out strategy for what to do if those happen to go off, because it technically could still be possible for them to go off, and we want to know what the system is going to do in those instances. We don't want to be in any case where the system doesn't have a defined behavior, and then, okay, the door is fully open and the closed sensor gets triggered. What does the door do? Oh, it starts closing for some reason, or or the door thinks it's fully closed at that point, but it remains open for some reason. Like, yeah, we want to be absolutely sure of what's going on at any given time for all possible inputs, ideally, and that's what it means to be a deterministic system. That's what makes a DFA. Every possible, it's not explicitly what makes a DFA. The fact that it's deterministic means that we're only in one state at any given time, but ideally that's the way we should be approaching this type of system, is to map out every possible input for every possible state. Good question. All right. Let's take a look at another system. We are going to look at some string recognition. So you might recall that, well, when we say string, we as computer scientists often think of like a piece of text, but in the context of a DFA or a finite state automata of any sort, a string is just a sequence of inputs into the system. So if we had a system that takes numbers, all numbers, and when we say recognizes, it means that the system is going to be in a final or accepting state once that sequence of inputs is received. Now, there's a couple things that we probably want to define around here. What do we mean by recognizing that string? Does it mean that the sequence of inputs that we receive contains that string, starts with that string, ends with that string, or is exactly that string? And I'm going to go with, unless you're told otherwise, it means exactly that string. So we want to have a 1 followed by a 2, followed by a 3, followed by a 4, followed by a 5, followed by a 6. How would we map this out in a DFA system? So I think the first thing that's worth noting is, what is our alphabet? Hopefully we recognize that our alphabet are the numbers 0 through 9. That should be fairly straightforward. How would we model a system that recognizes this string here? Let's take a couple minutes to have a go at that. Hopefully this one should be fairly straightforward, so I'm going to open up a post for people to put their suggestions in. Again, please ask questions in Piazza or Echo 360 if you have them.
If we want the system to reject a certain input at a certain state,
Mhm.
then we can just not fill in anything for that
Yes.
Okay.
Yeah. So the question was, how do we project a specific input into the system? There's a couple different ways that we can approach that. I know that we talk about having certainty in our systems, so you could have a terminating state where anything that doesn't match the input gets directed to go to this terminating state, and then all further inputs at that point remain in that terminating state. That's one approach. The alternate is that you could just let the system die. Now, as long as your system has a reasonable approach to what happens when you do get undefined behavior, and that is to say that the system like stops or shuts down or returns false at that point or something like that. As long as you have that, then in theory things are okay, but we want to be careful if we are setting up our system in such a way that a particular input is not recognized in a particular state, or is not present as a transition on any given state. Okay, question here. Since we have a string of 6 characters, does it mean we have 7 states, including the initial state? Absolutely, yes. And this is a common mistake that people make. They go, oh, okay, well, the first character is 1, so we initialize into the 1 state. And it's like, no, you don't initialize into the 1 state. You initialize into the I have yet to receive any inputs state. And then when you get the 1 that you're looking for, then you transition into the 1 state. Okay, so this one should be fairly straightforward. Since we are explicitly matching a string 1, 2, 3, 4, 5, 6, I made this one way too easy, that's okay. So initial state, we get a 1, we move to the first state, we get a 2, we move to the second state, 3, move to the third state. In this case, we're naming the states in such a way that it represents where we're up to in the string that we're trying to match against. So we're trying to match a sequence of 1, 2, 3, 4, 5, 6. Was it 6 or was it just 5? I think it was up to 6. We're trying to match a sequence of 1, 2, 3, 4, 5, 6. So when we initialize, we haven't received anything, so it's a null or an empty string or whatever you want. You could just say start. It doesn't really matter what you name the states, but it is convention to name the states that they represent where you're up to. So 1, 2, 3, 4, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6. And because we are trying to match a string and we're aiming for an accepting state, we use a double circle to represent that we are in a final or accepting state. And this really is as simple as this string matching needs to be. Initial state, if we get a 1, we move here. Any other input than a 1 when we are in this initial state, the system just stops altogether. Doesn't work anymore. We go away. If we get a 1, then we move to the first state again. Once we're in the first state, if we get anything that is not a 2, then the system is just going to cut out and die on us. But if we get a 2, then we move on to the next state, and it's only when we get the sequence 1, 2, 3, 4, 5, 6 that we end up in this final or accepting state. And if we were to query the system at this point in time, then ideally, because it's in a final or accepting state, it would be all like, oh, I'm in a final or accepting state, and we can go, okay, well, we're all good. We have matched or recognized this string. So what we're trying to do here is we're trying to treat words. So we've looked at this idea of like discrete individual events in like real world systems just as a sort of a primer, but one of the common things that we can do with this sort of modeling and this sort of system is we can actually treat data as inputs. So if you have a continuous stream of data, you can treat each of those pieces of data as an input to the system and action the system as if we are having those discrete separate inputs. So in this case, a sequence of numbers can be treated as a sequence of discrete events, and we can map this out in the same way that we might map out a system where we have actual physical buttons being pressed or physical sensors being tripped, that sort of thing. Hopefully we recognize that the alphabet for this system is going to be 1, 2, 3, 4, 5, 6, and that the set of states for this system is going to be 0, 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6. The initial state is going to be 0. The accepting state is going to be this, or the set of accepting states is going to be a set containing only this. And the transition function then represents all of these transitions between all of these states. Okay, NFAs. All right. I really should have chosen a better string for this one. Interestingly enough, the NFA is going to look exactly the same as the DFA for this. I should have chosen something with, hang on. Yep. Should have chosen something that contains multiple of the same thing in there. We are just going to skip right past that one. It's going to look exactly the same as the DFA. All right, let's try something a little bit different then. Let's look at an NFA to model a system that recognizes any string that begins with hello or hi. Let's take a few minutes, have a go at this. Remember, we're working with an NFA at this point in time. This means that we're going for a non-deterministic system. Non-deterministic system means, of course, that we can be in multiple states simultaneously. So we can map out our system such that we could be in multiple states at the same time. Let's go ahead. I'll put up a post for people to post their questions and solutions about that one. How'd it go?
I'm just thinking,
Hmm.
I did it wrong, but can I only branch off at the H level? Or are there other places for the state to enter, for the system to enter a non-deterministic state?
I mean, in a non-deterministic system, they could be completely disconnected if we really wanted them to be,
Yes.
or we could leave them connected. Hmm.
Because just to make it a better fit for me, right?
Mm.
Like from the starting node, I just drew out like two separate paths,
Mm.
each take input of each.
Yep.
Yeah. But
Yep.
then I was thinking about it, and I was like, oh, I don't really need to do that. I guess just merge them.
Yeah, I mean, in theory, you could just, it could theoretically. Oh my gosh, I should unpause the audio. Yeah. Yes, so there are a couple of different ways that we could approach this one, and in terms of how we start off, we could have a single starting node that splits, which semantically makes good sense. But in theory, we could also have two effectively disjoint graphs where you have two distinct separate starting points, one that recognizes hello, one that recognizes hi. And they're part of the same system, but they're effectively two distinctly separate systems. Let's take a look at both of those. How are people going on this one? Does anyone have any other questions they'd like to ask in the Piazza or in Echo 360? It's gone awful quiet over there. Oh, no, we have a question. Yes, okay, good question. So, the question is, how do we deal with the anything that follows hello/hi? Okay, so let's draw this system, well, let's draw out something that looks like this system. So, a couple different approaches. So we could start with an initial state, like so. Empty string, and then, so for an NFA, the nice thing about an NFA is because we can be in multiple states simultaneously, we don't have to worry about branching the same input, which is one of the things that makes NFAs really nice. So if I get a H or a H here, albeit they shouldn't really have the same name. I'm not going to actually name these, but we'll so we can have H in both directions, and then this one can be an E, L, L, and O. Whoop. So hello up the top, hi down the bottom there. And at this point, we're like, okay, we've had something that starts with hello, or we've had something that starts with hi. What do we want to do? Well, we want to loop and remain in this state for the entire alphabet, in this case A to Z. Something like that. So that's how we could illustrate that in a system like this. And we can shorthand this in the transition table as well, if we really want to. But the basic idea is, yeah, once we get to either of these end states, we just stay there because the condition has been met. If we were to flip this around and we wanted to say anything that ends with hello or hi, what could that look like? Well, that would look similar, but instead of that, we would have our starting state where we would loop and remain in the starting state at all times. and we still have our same usual thing over here. It's just that we wouldn't loop at the end. And this means that if we reach any of these accepting states, so the deal with the accepting states is as long as you are in an accepting state at any point in at the point in time that the string or that the input sequence terminates, then you're good. Yay for accepting states. So that's where we want to be, in one of the accepting states at the point that the system terminates. Now in a DFA, because you're only in one state at a time, that means you are in an accepting state always when the system terminates. In an NFA, you can be in any of the accepting states, and that's considered acceptable in that instance. So this represents a ends with, because if you get a H and then an I, you end up in this accepting state. But then if you get, a Z after that, for instance, then you drop out of this accepting state. But because you've remained here the entire time, if you get another H, you can then proceed back through this sequence here, and so on and so forth. Okay, I'll leave you all to have a play with the transition table and 5-tuple representations of those, but if anyone has any questions about the transition table and 5-tuple representations of those systems, feel free to ask them now, but hopefully they're fairly straightforward. One thing to note with the 5-tuple representation of an NFA, if we go back to this one, 5-tuple representation of an NFA, you will notice that Q0, there's two of them, isn't there? You'll notice that Q0 becomes a capital Q because you can potentially have multiple starting states, whereas in a DFA, Q0 is always lowercase because you can only ever have one starting state in a DFA. Okay, so then the question is, how do we translate this down to a DFA? We have an NFA, we translate, how would we translate this to a DFA? First of all, let's just draw out a basic DFA. If I had asked you to draw a DFA of this system as opposed to an NFA, what would that look like? Bearing in mind that you can only be in one state at any given time, and hopefully this would make reasonable sense to everybody. If we were to draw out a system like this, we'd start with the empty state, and we would see where the strings differ from each other. So if we get a H, and then they both start with a H, that's nice. And then if we get an E, we go up to, and if we get an I, we go down to here. And this was our finishing state there. And we have the A to Z there as the rest of our inputs, and then we would fill out our hello that way. It's like, okay, well that's how we would do this if we were just going straight to a DFA in a system like this. So the question is, how do we convert an NFA? Because there is an actual procedure for converting an NFA down to a DFA. And the way that we like to do that is by using the transition table the way that I like to do that is by using the transition table. You might like to do it a bit differently, depending on your own preferences. I like to draw up a transition table. So I'm going to give each of these states a name. This is going to be Q0, Q1, Q2, Q3, Q4, Q5, Q6, and Q7. Okay. And for argument's sake, that's an O, that's an I, and then that's everything else, excluding those. I should probably write it as as not just A to Z, because A to Z is a set that includes each of these, but this should be the set of just all other inputs that are not these ones here. All right, so if Q0 is our initial state, let's draw this out as a transition table. So then we have H puts us into the set of, let's add all of these in Q1, Q2, Q3, Q4, Q5, and Q6. All right, H puts us into a set consisting of both Q1 and Q6. Q1, Q6. That's a little bit hard to see, but state consisting of both Q1 and Q6. Okay, Q1 with a H does nothing. Q2 with a H does nothing. In fact, the rest of these do nothing. This will be a very sparse table. Okay, with an E, if we are in Q1, it takes us to Q2. And again, the rest do nothing. If we are in an L and we are in Q2, it takes us to Q3. And if we're in Q3, it takes us to Q4. And the rest do nothing. And if we have an O and we are in Q4, it takes us to Q5, which is an accepting state. And the rest do nothing. And actually, it's probably worth noting, maybe not the rest do nothing. This would be Q5 still. This would be Q5 still. This would be Q5 still. And this would be Q6, Q6, Q6. Because no matter what you get, you want to stay in that state once you've gotten there, right? Because it's the string that starts with. So once you've started with it, you want to stay there. So in fact, we can write that across the board. We can Q5, Q6, Q5, Q6, Q5, and Q6, and rest there. And I, if we are in state Q, oh wait, no, there's a 7. I've missed Q7. I've messed that up royally, eh? Okay, Q7. Just got this all out of order. So Q6 with an I puts us in Q7, and everything else goes away. Everything else goes away. So that's our transition table. Fairly sparse transition table, but basic transition table. Now, if we wanted to convert this from a NFA, which this is an NFA because we have this one place here where we're dealing with multiple states simultaneously as the output from a single transition. So what we do then is we remap the entire table starting at Q0 and building out from there. So H, E, L, O, I, and then the rest. Okay, so Q0 remains the same. That's our initial state. That's all good. But then we treat the combination of states Q1 and Q2, because again, this represents being in simultaneously being in states Q1 and Q2, because if we're in Q0 and we get a H, it puts us in both of these at the same time, which in a system where remembering that the whole point of what we're trying to do with mapping out our systems in this way is that we are trying to end up with a deterministic model, because computers are deterministic by their very nature, so they cannot be in multiple states simultaneously. In theory, in this sense of model, we always want to be in a single state at any given time. So if we are going to build off of a non-deterministic model where we have the ability to be in multiple states at the same time, then we need a way to map it down so that we are only in a single state at any time. So in theory, we go from Q0 and we get a H, and that puts us in both Q1 and Q6 at the same time. So what we do then is we say, okay, well, let's just pretend that being in Q1 and Q6 at the same time is one state. So we're going to create a new state. I'm going to call it Q1, Q6. Note that I'm not using the curly brackets and the comma here to denote a set. I'm saying this just happens to be a state which I happen to name Q1 and Q6. So Q0 with a H puts me in Q1, Q6. And then we map out from there. We go, okay, well, if I'm in state Q1 and Q6 and I get an E, what does that do for me? So if I'm here and I get an E, well, an E from Q6 does nothing. It goes nowhere, so Q6 just disappears. An E from Q1 goes to Q2. So Q2. Now a H from that goes nowhere. An L from there goes nowhere. An I puts us into Q7 from there. And the rest of these go nowhere. So then we look at this next row of the system that we have and we go, okay, do I see any new states here that I haven't seen before? Yes, I do. I see Q2 and I see Q7. So then I'm going to map out Q2 and Q7. So again, Q2 with an L goes to Q3 and everything else is blank. Q3 is new. I'm going to add it to my list. Everything else is blank. Let's do Q7. Q7 with anything goes back to Q7, and Q7 is an accepting state. Now, if Q7 was like several states, it would be if that several states contained an accepting state, we consider it to be an accepting state as well. But that's just going to map onto itself. Okay, that's fairly straightforward, hopefully. Q3, and if we get an L from Q3, we end up in Q4 and everything else is blank. And that adds Q4 into the mix. And Q4, if we get an O, we end up in Q5. Yep. And everything else gives us a blank. And Q5 is an accepting state. And it just loops back on itself for all inputs. Okay, and that's our transition table. And if we were to consider the DFA for this system, you'd find that this effectively looks quite similar to the DFA that we had before, because if I was to rename these states to something else, so if I was to call this naught, if I was to call this H, if I was to call this one HE, this one would be high. And this one. You'd find that this comes out looking pretty much exactly like this. Now, they don't always come out looking exactly the same. Sometimes they come out looking like weird and convoluted and have extra loops and things in them, but by taking this stepwise process to performing a conversion, we can take a non-deterministic system, any non-deterministic NFA, we can always get a consistent DFA out of the system at the end, and that's something that we can consistently program. Any questions or thoughts about that one? All right, now we are running out of time, but we could potentially take a run at this depending on how we're going, or we could leave this as a challenge and see what people want to do with it. And let people have a go on their own. I think that's what we'll do. I'm going to leave you all to have a go at this one, by which I mean ask your questions now and after the session in Piazza, and we'll see how we go with it. You've already seen a little bit of an example of what a system that ends with a particular string looks like. This one gets a little bit interesting because we have some overlap, and we have some overlap between the top string and the bottom string because it's a simpler string consisting of just 2 characters. So we're going to run into some places where the strings overlap with each other. Hopefully this example gives us a nice idea of where having an NFA representation really shines, because you'll find that if you try to map this directly as a DFA, which I encourage you to try, things start getting a bit weird when you have to map between them. It gets very easy to make mistakes when you try to map this directly as a DFA. So for the next 5 minutes, give this a go. Post any solutions that you get in Piazza and feel free to ask any questions. And we will revisit this one at the start of next week's lecture. But yes, for the remaining 4 minutes, if anyone has any questions that they want to ask, any questions about any of the things that we've just worked through, or any questions about this particular exercise here, please go ahead and ask them. Or even just any comments or general thoughts about them. Thoughts on your end?
I'm just trying to think. I think I'm still stuck on like if we have 2 separate branches, right, and there's some overlap between them, then I'm considering what the benefits, what the consequences of merging and not merging the overlap part is. I think this is just what I have in my head, but let's say for processing a string, like recognize the string or whatever. Then if both branches start at the roots, then effectively you could merge or not merge them where it overlaps, and that should be fine.
Yep.
But if there's an overlap and there's some differing string before that overlap, then I don't think you can merge that overlap, because if you go, you could potentially go through one branch, process that branch, and then because of the overlap, you go into the second branch. Then you've kind of jumbled the words you're trying to.
Yeah, and that's where you have to be careful with the. It can be tricky getting the overlap right if you try to develop a system with an overlap at the start. I should turn my microphone back on properly. Yeah, so if you're trying to develop with the overlap between multiple strings at the start, it can be tricky to do that well. That's one of the advantages that we get from the NFAs, is that we don't have to have that overlap at the start. We can just say, okay, all right, here are the 4 different strings that I'm mapping to, go, and point it at all of them, and anywhere where there's any overlap, the NFA sort of automatically takes care of. Then once we have our NFA figured out, we can perform the down conversion, and we end up with a system that we can guarantee well, we end up with a DFA that we can guarantee correctly handles that overlap, because the DFA will account for the overlap occurring between multiple strings. It eliminates the possibility of there being mistakes in the DFA logic, provided that we've done the conversion correctly. Whereas if we try to go directly to a DFA, then we can potentially run into cases where we try to map the overlap ourselves and we miss cases, which, when I've gone over this course many times in the past and I've been working through DFA examples, I have made that mistake so many times. It's a very easy mistake to make, yeah. Question is asked, do we have 2 branches? Yeah, you probably should have 2 branches. That's a good way to go, absolutely. At least for the NFA. For the DFA, things might get a little bit weird and different, so you might have to play around with that a little bit if you try to build it directly as a DFA. And I encourage you to try both building it directly as a DFA again and developing as an NFA and seeing how they compare, and then seeing how the down conversion compares between the one that you've created from scratch as a DFA versus the one that you've down converted from an NFA. Absolutely. Okay. Can we have a loop back to the initial state after reaching an acceptance state? Yes, if it makes sense, absolutely. Absolutely, yeah. Okay, well, the exercise, the question is, so it's any string that ends with those things. So it says if the string is 01111, should the system only recognize the end of the string, which is 1011 in this case? Yes. It's not that it should only recognize the end of the string. The idea is that if we're trying to recognize any string that ends with that sequence, then having hit that sequence at that point in time, the system is recognizing the string as having correctly ended with that sequence. If any further characters were to be received or any further inputs were to be received at that point in time, then the string no longer or may no longer end with that valid sequence, and it should leave the accepting state at that point until it once again ends with that sequence. All right. That's time, everyone. Thank you all very much. We will revisit this one at the start of next week. Thanks for bearing with us through the technical issues that we had at the start as well. And we're all good to go for next week. No more technical issues, fingers crossed. But we're definitely all set now in terms of all the settings and everything. So yeah, we'll catch you all then.